All right, so I left off on part one talking about recurrent neural networks. So these are for sequential data, primarily time series data, but also textual data. And I talked about how they unrolled the time steps, basically sending the input to the neuron, which, as we recall, has one of a number of nonlinear functions, which we'll talk about here in a couple of slides. And it processes that and it sends an output, but it also sends a signal or a weight to the next time step. And so this is what it, I guess, physically, if you will, looks like. But functionally, it looks like this, where we take this weight that is passed from one step to another, and we basically pass it forward. So at step one, which might be the first of your readings for temperature throughout the day, you send the input. You perform the function, you give the output, and you also send some kind of signal or a weight to the next time step. Maybe if your temperature is every hour, this would be 8 o'clock, this would be 9 o'clock, this would be 10 o'clock. And so we're sending some kind of signal forward in time from one reading to another. And this is exactly like the weights that we see here. It's exactly the same kind of weight where it's just some kind of matrix. That's a multiplier that gets sent from one step to another. But ideally, if the network trains well, that multiplier represents some kind of pattern that occurs across time series data. And so, like I said, this could be some kind of set of heart rates over time that indicate, arrhythmia or whatever kind of patterns are relevant in the time series data. But ultimately, this is how these recurrent neural networks are better suited to sequential or time series type data than a regular dense neural network, because regular dense networks don't have this conception of sort of periodicity or of the sequence of data. They really just look at the features you give it and don't really care what comes before or what comes after. But this specific type of neural network does gain an understanding of the features from one reading to another. This does, as kind of a side note, make train test splits more difficult because you can't really randomize the data. You can't really split it randomly. You have to keep the sequences in order for there to actually be sequences for this to learn from. But there are definitely ways around that. Honestly, usually folks just cut off the last however many days or weeks of the data and use that as a test set because the most recent data for time series is usually the most indicative of the future data. So it's the most realistic accuracy. Recurrent neural networks we won't be implementing, we won't be using, so I won't be testing you over them. They're conceptually a little more sophisticated than some of the others, but I thought it was at least important to give you the opportunity to hear some about them. So if that didn't make a ton of sense, you don't have to worry a lot, because like I said, we won't be actually getting hands-on with these specific types. So I'm going to skip this slide, which is about the inner workings of the cells that we saw in the last slide. Not going to go into that. So let's talk about training. So I've talked about these weights. So if we skip back again to slide 8, I've talked about these weights from one layer to another, right? So every one of these connections from the inputs to the hidden layer, from the hidden layer to the output layer, these are all weights, which basically just means they're a multiplier, right? So this input, whatever it is, 0.58, gets multiplied against something, 0.2, 0.15, whatever. It's usually between 0 and 1. And it gets passed on, and then this function is applied, and then it gets multiplied by a weight, and then this function is applied, and it makes a prediction. And so those weights are how the neural network learns to model the input. So it increases the weights whenever it increases accuracy, and it reduces them whenever that reduces accuracy. And so how does the network know what the best weight is? How does it develop the ideal weight for each of these layers and for each of all of these, what in practice become millions of connections as you have many inputs, many layers? Well, that is an optimization problem. So we basically take the network and we randomly initialize all of those weights. We randomly initialize all the weights connecting all of the layers, and we basically just make a guess. And usually the guesses start out, if you think about this as the multi-dimensional space of just the model and the data, we start out with a very high loss. That's this red right here, is we're basically saying, hey, we've randomly initialized all of these weights, and we just run the data through, which means the guesses are basically just random. They're obviously not going to be very good because we're guessing with weights that have not been trained on any data. And so we have a very low accuracy, a very high loss. Basically, our guesses are not very good. And so we take those guesses and work from the top down. And so we try to get from this very high loss or very low accuracy, basically a very inaccurate model, one that guesses house prices very poorly or guesses iris species very poorly, to one that's down here, which has a very low loss or very high accuracy, and it's guessing very well, basically. And we do that, like I said, by randomly initializing all of these connections just to a random number. And then we make a guess all the way through. And here we see at the end how wrong were we. Did we guess a 2 when it should have been a 1? Or if this was house prices, did we guess $5,000 over the correct guess? And we take that guess and basically work our way backwards by saying, well, if I guessed a 1 here and it should have been a 2, then what led to that incorrect guess, right? Was this weight from this layer to the one before it too high? Was this weight too low? And if so, then I decrease this one and I increase this weight. And then I look at the connections from this neuron back and say, well, maybe I need to increase this connection and decrease this connection, and then so on and so forth for every one of the connections from every cell to every other cell. So we basically look at the guess that the random network made and work our way backwards to say, well, what changes can I make to all of these weights between all of these layers that make the model more accurate? And we do that over and over and over again, usually working our way through the data several times. So we usually iterate through several what are called epochs, where we look at all of the training data. 10 epochs is pretty common. So basically we look at all of the training data 10 times and continuously refine the model. And that model refinement kind of looks like this random walk down, where we start out at a very inaccurate place in our models space, and we make a slight improvement, and we make a slight improvement, and we continue making slight improvements until we can't anymore, and we reach this minimum or basically the most accurate the model can get without starting to overfit and getting worse. So neural networks are provided training instances and connection weights that would produce a correct output or strengthen. So that's what I just said. So basically the neural network looks at the data, it looks at the training data, and it strengthens the weights that would provide a correct answer, and it weakens the weights that led to an incorrect answer, and it does this over and over and over. Training deep networks presents a unique challenge because weights must be adjusted in each layer according to their contribution to the output. And so this backpropagation algorithm is exactly what I was just talking about, where we start at the output and we look at all of the weights that contributed to the correct or incorrect answer, and we tune them, and then we work backwards from layer to layer all the way to the inputs, and that's backpropagation. We're working from the top backwards, back down through the network. Making it more accurate with tweaks. So backpropagation works from the output backwards, what I just said, through the network, evaluating each weight and its contribution to the gap between prediction and ground truth, adjusting accordingly. So that's it. It looks at how incorrect was the answer. Was it too high? Was it too low? And raises it or lowers it accordingly. So activation functions. So we talked about the linear threshold unit, or the LTU, and so I'm not going to test you on activation functions, and we're basically going to accept the defaults. There's only really 2 that anybody uses, and that's this ReLU and this sigmoid. And so sigmoid is very good for guessing classes of data, like we would use sigmoid for guessing the iris problem. And ReLU is very good for regression or for hidden layers because it's very easy to calculate. And so we talked about that linear threshold unit, or LTU, That is a very primitive version of these. So we would use these nonlinear functions in each of these neurons as our multiplier. And so each of these layers would be an LTU, which basically, or would be a ReLU, sorry. Each of these would be a ReLU, and each of these would be a sigmoid activation function. And all that it means is we sum up all of these inputs and we apply this, basically this equation to it, this ReLU, which basically just after 0 it just increases linearly, and then sigmoid, you can see, basically has diminishing after. It basically provides us a good 0 or 1 by diminishing everywhere past these. The reason, and again, I'm not going to test you a bunch on these nonlinear functions. It's just important to see them and at least understand the function that they play, like why we need them. But at the end of the day, we need a gradient. And so whenever we were talking about how we train these models, right, I have to say, well, how incorrect was the model? And whenever I'm doing that, I basically have to say, well, this neuron right here was 5% too high, right? This was 5% too high, or it was 20% too low, or whatever the case was. And I do that with these threshold units. These threshold units basically provide me a nonlinear way to calculate the gradient, or the direction in which I was incorrect and how incorrect I was, right? And so I use these to basically say, on this ReLU, for example, if I'm saying, well, my prediction was too high for the house prices, I look at one of the neurons and I see, well, maybe it was coming out at an 8, or whatever the output was, right? And so I say, well, I obviously need to dial this back, and so I need to decrease it, and I can calculate the gradient to see which direction and how much I need to decrease it, right? And so maybe I calculate, well, I'm too high, so I need to go in this direction. I need to bring it down to a 4, and I take that step down by modifying all the weights from that function. Sigmoid functions provide a non-zero derivative everywhere, so that derivative is how I train them. That's the gradient. Linear function ReLU is continuous but not differentiable at 0. It's commonly used because it works well and it's fast to compute. It's faster to compute this than it is the sigmoid or the hyperbolic tangent. And linear isn't super useful because I can get too far out here in the negative territory that makes my neuron useless. Anyway, like I said, I'm not going to train you on the gradients or the activation functions, because for most of the time we will just use the default, kind of like we did with scikit-learn, of all the default, like kernels and things like that. The default in this case will be ReLU, and we'll just use it because it works. That's why it's the default. But every now and then we'll have to specify sigmoid, and again, that's because sigmoid is very good at guessing classification problems. All right, so TensorFlow. So we're going to be using something built on top of TensorFlow. We're going to be using Keras specifically, which makes it very easy for us to get into TensorFlow. So TensorFlow was actually open sourced by Google. It's a Python project. It's really what popularized deep learning for most people. So now deep learning is much more accessible, and that's because Google open sourced TensorFlow. And TensorFlow works in Python, and it was written in C++, I believe. And so it's kind of become the dominant framework, but it's definitely not the only one. It was built on the concept of an execution graph. So we basically we're going to write some code, and it's going to populate the graph, and then we're going to tell it to run, and it's going to run all the code. And so thus far, we've been running things that whenever we told it to go, it actually executed the code. TensorFlow doesn't work like that. You basically tell it all the things you want to do, and then you tell it to run it, and it runs them. And so TensorFlow can be kind of hard to figure out why you're having problems sometimes, because you've written a bunch of code that it hasn't run until the very end, and so your problem could be halfway up the code, but you didn't know you made an error because it didn't actually run anything. It just built this execution graph, and we'll see kind of how that works. Tensor objects are passed between operations in the graph, hence TensorFlow. And so basically, a tensor is just a matrix. It's just a matrix or a vector. So it's an abstraction, and so they just call it TensorFlow because it moves tensors or matrices from one step of that graph to another. Tensors are objects in the Python API. So Python API is really just the API is just the interface. We've been using the Pandas API, if you will, so far, and it's an application programming interface. And so that's actually how we've interacted with all of the libraries so far. So TensorFlow is just another library that we'll be working with, just like Pandas is, right? And so it just has different operators that we'll find, kind of like we've done with the PD dot and tab. TensorFlow has similar types of functionality. But anyway, tensors are actual objects. So like in Pandas, we had the data frames, which is how our data is read and stored in memory. Tensor is like a TensorFlow data frame. It's the way that it stores and moves data. Tensor is also a mathematical term for n-dimensional arrays or matrices. So that's what I said. It's basically like matrices and vectors is a tensor. And so they move tensors around with this, which is why it's called TensorFlow. We will be using something that runs on top of TensorFlow. So again, I'm not going to test you on this, but you can think about TensorFlow has really low level interface where you can do basic matrix multiplication. They have a higher level one that wraps some of that in more convenient functions. And then we'll be working in what's called Keras, which is the highest level. And it automates a lot of work for us that if we were doing this TensorFlow-based API, we may have to write 200 lines of code that in Keras would be 10 or 20, right? And so that's why people really like Keras, is because it makes TensorFlow easy to use. That's the bottom line, is Keras, it makes TensorFlow easy to use. It actually makes it so easy to use that it has been built right into TensorFlow now, whereas it used to be a separate standalone project. I'm going to skip all the way to the end because these slides about MNIST we'll actually see whenever we do this hands-on, and we'll walk through a notebook. And so let's talk about some of the challenges. So vanishing exploding gradients is what I alluded to. We won't have too many of these challenges because we're not going to build very deep networks, but basically we can get those multipliers on the neuron weights so that they're way too high or way too low, and a neuron function becomes dead, where we can't modify it to any practical degree because it's negative 9,999, and any step toward training those weights or tuning those weights would just take almost infinitely long to come back from, and that's just because these things can continuously get pushed too far in one direction. It doesn't make sense, basically. That's been solved by things like ReLU, which is that activation function we talked about, and smaller training steps, not taking really big steps in the matrix weights. We talked some about exploring the hyperparameter space. Basically, these are all of the things you could set about a model, and there are a lot of things you can set about a model. So it can be really hard to find the optimal model design, the optimal number of neurons, the optimal number of layers, and activation function and training step size. All these things can make a reasonably large difference. And because it can take hours or even days, so some of the biggest sophisticated image recognition networks can take over a week to train on a cluster of GPUs. It can be really hard to test different permutations of that whenever it's very expensive and very time consuming to train it. So it can be kind of problematic to know for sure that you have the best network. And so that's why there's kind of an art and a science to it right now, is getting an understanding of which networks tend to work best for which problems. Scaling across GPUs. So I haven't talked a ton about GPUs, but it turned out that Google figured out that GPUs were very good at doing deep learning calculations. And it's actually the adoption of GPUs in deep learning that has really allowed it to take off. And so GPUs are the graphic processing units. They're the video cards that play video games, basically, and do some 3D rendering. And historically, they've been developed to play video games, to render images, right? And the work that requires is basically a bunch of small computations. So video cards are very good at making millions or trillions of small calculations every second, whereas your processor in your computer is better suited for fewer more difficult calculations per second. And so most computers have 4 processor cores. A lot of the GPUs have 1,500 or more. And so that allows GPUs to do a lot of parallel tasks, which is exactly what deep learning involves. It involves a bunch of small calculations to matrices, because those matrices are all the weights that we've been talking about this whole time. And so we need to do a bunch of small calculations to figure out how we need to tune them to make the model better or to make the model more accurate. And GPUs can be several orders of magnitude faster at doing that than CPUs, which has unlocked a whole new, which has made deep learning much more accessible and much more successful. And then optimizing networks. So basically, we're not going to have to worry about this because we're not going to build really large networks. But Keras doesn't produce optimized TensorFlow code. And so for really sophisticated TensorFlow development shops, they actually have to go in and write code that looks different than everybody else's to optimize the networks and the training. For most users, that doesn't really matter because it's not worth it. You just spend more money on GPUs and less money on developers, and it's worth a while. But for really large companies like the Googles of the world, the Amazons of the world, it makes sense for them to go in and actually optimize this kind of code. So anyway, those are some of the conceptual underpinnings. Like I said, I don't intend to test you on that. But it is important to understand some of the concepts, because what we'll be doing next week, or actually the week after, so what we'll be doing after the midterm is actually building some machine learning models using deep learning. So we'll be able to use some of the different concepts that we've been working on. So we'll have to still prepare the data with pandas, and then we'll still have to do things like computing it and scaling it, and then we'll be able to apply these deep learning models. Which are just another form of machine learning. And so it's important to at least have some of the concepts that underpin it. All right, if anybody has any questions about this or the midterm, don't hesitate to send me an email, and I'll be happy to reply. Thanks.